Hello and welcome to Dr. T's Math. In this video, I will discuss factorials, the multiplication principle, which extends from factorials to permutations and combinations, and also applies to probability and statistics, the multiplication principle, and then permutations and combinations, and we'll do some examples of each of these things. So factorial is when we multiply a number times that number minus 1 times that number minus 2 times that number minus 3 and so on all the way down to 1 like this, 5 times 4 times 3 times 2 times 1. And as a matter of mathematics, that's simple and sort of arbitrary, but as with all of the different things that we're doing in math, they have practical applications in physics and science and just figuring out our physical world. And in this case, it's with combinations. So like, say you had a bunch of books, and you want to figure out how many ways there are to arrange those books on a shelf. Say you got 10 books, and you want to figure out, well, how many different ways can I put those 10 books on a shelf? Well, it's 10 factorial, which is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And let's see what that is. 10 factorial. Most calculators, or I should say some calculators, will have a factorial. Let's see if these do. There. And so we're going to be at 10 over here to function 10 factorial. That is 3,628,800 possible ways to arrange 10 books on a shelf. And maybe that's not so exciting. So you want to know, maybe you're a betting man or woman, and you want to know, well, how many different ways can those horses come in at the track? Well, if there's 10 horses, then it's that same 3 million ways. And so if you were to try to bet on the exact order of the horses, then you would have like a 1 in 3.6 million chance of getting that correct. Which would be high yield in the betting world because you have such low chance of winning. The multiplication principle is when we have kind of a combination event, a compound event, or a compound situation. Say we had 50 boys and 50 girls, and we want to figure out how many different combinations of boys and girls are there. Well, let's put all these boys in a row, and so there are 50 ways that we can put the first boy, and then after we put the first boy in the row, there are 49 ways we can choose, 49 boys to choose from, the second boy in a row, and then there are 48 and so on all the way to one way to choose and organize the last boy in a row. And the same goes for girls, which is going to be 50 factorial. And so if there are 50 factorial ways to arrange the boys in a row, that means, how many are there? Oh, that's way too many. So this is an inconvenient number to count out how many zeros there are here, and then to put that back into the slide there. So there are 50 factorial ways to arrange those boys in a row, and then that's going to be multiplied by 50 factorial ways to arrange the girls in a row. And so we've got this many possible boy-girl combinations, and that string of zeros just goes on and on and on. So it's a lot of different possible combinations. And that has actually a lot of meaning in a large population over time. So that's the multiplication principle. You can use it for, again, when you have two different events or two different sets going on where you need to figure out how many ways are there to arrange something, or how many different pairings can there be among these two discrete groups. First, figure out how many ways there are to pair or to arrange the elements of the first set, and then how many different ways are there to arrange the elements of the second set, and then multiply those together. Next up, permutations. Permutations are just a further application of factorials, and then combinations apply factorials and the counting principle. And so when order matters, for example, you've got 100 applicants for some job, and you want to know how many different ways can you choose 10 of them. And your first choice is going to be distinct from your second choice, it's going to be distinct from your third choice, and so this means order matters. I'll give you another example in a moment here. So if you've got 100 total, that's your n, and then your r is you're choosing 10, and so this is just 100 factorial divided by 100 minus 10 factorial, which is 100 times 99 times 98 times 97 times 96 times 95 times 94 times 93 times 92 times 91 times 90 times 89, and so on all the way down to 1. The 90 factorial on the bottom here, 100 minus 10 factorial, is going to be 90 times 89 times 88, and so on. And so what's convenient sometimes about these factorials is that you don't have to deal with huge numbers, even though it seems like, well, that's going to be a huge number and that's going to be a huge number. But you can eliminate common factors. So in this case, it's actually from 100 to 91, which is still a large number. Let's see what we get over here. On your calculator, you can type in 100 NPR. Oh, no, it depends on the calculator. In this one, we're going to have to type in first NPR, and we'll do 100, comma, 10. And that's a large number there. So let's see, 1, 2, 3, 4, 5, 1,000, million, billion, trillion, quadrillion. What's this? These are extremely large numbers. Right, so let's try to figure out a more practical application that most people can maybe understand, rather than just some generic 10 applicants from a job pool. How about there's a race on the track, and there are 8 people who are racing, and so we've got a track, and there are 8 lanes. I'm not going to draw all the lines, but there are 8 lanes. And so we've got these different people racing in each lane. And we want to know, well, how many different ways can we have first, second, and third finishers on the podium? And again, this probabilities and sample space and these types of things, the number of possible outcomes and the chances of one result are highly related to math that will help people make bets. I don't personally endorse betting. In fact, I advocate against gambling, but it gives us a perfect opportunity to teach statistics and probability. And upon learning statistics and probability, one should feel that gambling is sort of a silly enterprise, because people who make bets are almost sure to lose, or the probability of their losing is definitely much greater than the probability of their winning. Anyway, so we've got eight runners, and then we've got 3 different people on the podium, so that's our R value there. So what we're going to have here is 8 times 7 times 6, because we're going to have 5 times 4 times 3 times 2 times 1, and that's just going to cancel out that top part there. And so order matters, because first is definitely different from second, and a silver medal is definitely different from third. So order matters. 8 times 7 times 6. 8 times 7, 56. Times 6. We got 36 and 300. So we're at 336 ways to have 3 people on a podium from 8 runners running around a track. Lastly, looking at combinations. Combinations order does not matter. So we're going to have fewer arrangements, or fewer possible outcomes or pairings or whatever. as compared to the permutation. And CR can be phrased a couple different ways. You might see it like that. You might see it in parentheses. And then you might also see it vertically as such. And it's the same basic idea. Say we've got some cars in a lot, and we want to choose 3 of them to put out in the front. And it doesn't matter, we're going to put one in one corner of the lot, one in the middle of the lot, and one on the other corner of the lot on the road for advertisement or something. And it doesn't matter which order those cars are displayed. We've found that, or that the auto dealership has found that the marginal benefit of swapping order of these things is negligible. And so people are going to respond to that passive marketing there with these cars on the road as they pass by. So order doesn't matter anyway. So we've got, let's say we've got 100 cars on the lot, and then we're going to choose 3 of them. So that's going to give us 97 factorial, 3 factorial. And so you can see we're dividing by more things on the bottom, which means that because we put that more on the bottom, then it's going to reduce the total number of possible ways to do that even more. That's going to be a large number, obviously. Let's think of one that is more like what you might see in tests and things like that for your students out there. So say you've got some options on a menu. You're gonna build a sandwich or something. You're gonna build a pizza, and there are 6 different toppings on the pizza, and in this particular price range, you get 3 toppings. Obviously, if you choose pepperoni, mushroom, and onion, or if you choose ham, pineapple, and green pepper, or if you choose bacon, ground beef, and sausage, whether you say ground beef, bacon, sausage, bacon, ground beef, sausage, bacon, sausage, ground beef, sausage, bacon, ground beef, these are all the same thing. You're going to put those 3 things on the pizza. So order doesn't matter. And again, green pepper, onions, and pepperoni is the same as pepperoni, onions, and green pepper. It's just the same 3 ingredients. So we're going to have 3 factorial on the bottom, which means we've got 6 times 5 times 4 times 3 times 2 times 1, over 3 times 2 times 1 times 3 times 2 times 1. Cancel out our common factors, and we're going to get 20 possible pizzas at a joint where there are 6 different toppings, and so for whatever this price range is, you're going to get a choice of 3 toppings. We can do then 20 different pizzas. So you can go there 20 days in a row. You have 20 different pizzas in a row, and you're not going to have the same toppings on any pizza. All right, well, this has been Adam, Dr. T's Math. Thanks for paying attention.